Hi guys, Matt here. Today I'm going to show you my code to calculate the ratio distribution. I already have code that calculates the addition of two random variables, continuous or discrete case, product distribution, so two random variables being multiplied, continuous and discrete case. For ratio distribution, I now have code that does the discrete case. Should be easy to expand to the continuous case. I'll probably do that over the next few days. Basically what I did is just implement this integral. You calculate the joint distribution between two random variables, and then you run this integral, and it's not too bad. Joint distribution, probably the most complicated part of it. So this is when you have a random variable z that's defined as a random variable x divided by a random variable y. You solve this for x, that gives you x is equal to z times y, which comes up in the indexing for the joint distribution. So let's get to the cool stuff. What just happened to it? Okay, so this is for the binomial case. Oops, crap. Hold on. Let me clear all these. I have too many things plotted, and I'm gonna get confused if I don't redo it. Okay, so right now the computer's re-plotting it, rerunning the calculations for the ratio distribution. Here it is. So first, we start off with the distribution of the random variable x. So in this case, I gave it a binomial distribution centered at with probability of success of 60%, 0.6. I replicated 100 times, so it should peak at about 60. Random variable y gave it a distribution with probability of success of 10%, replicated 100 times, so it should peak at about 0.10, which it does. Next, we calculate the joint distribution. Where it says joint xy down here, that's actually the x variable, and going into the screen's a y variable, and z is the joint frequency for the joint distribution. So it peaks at about 60% along the x-axis, 10% along the y-axis, so that looks about right. Then going back to the z, the distribution for x divided by y, that should peak. It's reasonable to assume that it should have a central tendency of somewhere around 6, because you have a distribution centered at 60 divided by 1 with a mean of about 10. So 60 divided by 10 is about 6. So it looks like it does. So let's zoom in for a closer view. And it actually, in fact, peaks at about 0.5, not 0.6. And we can verify that if we look at the data. Where the mouse I'm using right now is really touchy. I don't like it. So if we look at this, the highest value is actually at 5. 6 is up there, but 5 wins in this case. So what if we did something else, like a distribution centered at 80 divided by 1 centered at 40? That should peak around 2. So we can run that. It's not a big deal. Let's find out what happens. So we let it run, and in a second it peaks at 2. We can verify that by looking at this. It definitely peaks at 2 because we have E0 right there and negative E's above and below the second index. So you can play around with it, do any combination you want. Now let's run it for the Poisson distribution. So that was binomial. That's pretty easy. There's actually formulas derived for that already, for like the odds ratio. What you can do with this now is you can calculate odds ratio, because that odds ratio is in a 2 by 2 table. It's the first element in the first row divided by the second element in the first row divided by, it's A divided by B divided by C divided by D. So anyways, let's move on to Poisson because it's a lot more interesting. Too many plots. Okay. Where am I? Okay, Poisson. So now I did a Poisson distribution of lambda 80, so it's going to peak around 80. Poisson's not symmetrical. It's even more skewed than binomial. So I don't know, its central tendency somewhere around 80. Then I did one around 20. So now I'm going to do the ratio of the 81 centered at 80-ish. I'm going to use the word centered, divided by the 1 centered at around 20. That should give me a distribution centered somewhere around 4, because 80 divided by 20 is 4. I don't know exactly the distribution. It won't be Poisson, but it'll have similar shape to it. So here's the joint distribution of x divided by y. So you have the one centered at 80. You can definitely see it peaks towards the right half of the graph. And one centered at 20. You can definitely see that it's closer to you rather than deeper in. Then if we calculate the full joint distribution, we get this. But we know it's going to peak at about 4. So let's zoom in. So as we can see, it peaks at 4. And we can verify that by looking at the numbers. And it peaks at 4. Oh, no, it peaks at 5. Wait. 1, 2, 3, 4, 5. Am I misreading that? No, it definitely peaks at 4. I've been staring at the computer too long today. If we want to verify that the joint distribution integrates to 1, we can. That's what this says. There's a lot of round-off error in these calculations, but it's correct. Approximately correct. So that's the ratio distributions. Bye.